So in this video, I'm going to take what we have learned about probabilities and what we've learned about counting using combinations and combine them to help us solve some probability problems. And so just as a reminder, so when we when we solve for any probability, we're usually taking the number of successful outcomes, which expresses n of A, and dividing it by the total number of outcomes, which is n of S. So let's look at a few examples, starting with example 1. To win the grand prize in a fundraising draw, you need to match 7 numbers from 1 to 15 without regard to order. Part A. What is the probability of winning the grand prize? So let's look at how we calculate n of A. And so I'm going to write down here n of A is equal to, so if I were to count the number of ways to win the grand prize, you have to match all 7 numbers. Okay, so you have to match 7 of your numbers with the drawn 7 numbers. So it'd be 7, choose 7 if I were to express this as a combination. So this represents getting all 7 numbers. And then the total number of outcomes, n of S, is equal to, well, I'm going to choose 7 numbers from 15, because there are 15 from 1 to 15, so 15 choose 7. So then the probability of your event A, the A being that you're going to win the grand prize, using the probability formula, n of A over n of S, is equal to 7 choose 7 over 15 choose 7. It's going to be an incredibly small number. So that's going to be equal to 0.00016. So even a less than 1% chance of winning. Part B, what is the probability of winning second prize, which requires matching 6 of the 7 winning numbers? So the number of successful outcomes would be, well, I'm going to choose out of the 7 winning numbers, I'm going to have 6 of them, so 7 choose 6. Multiplied by 8 choose 1. So this part here represents the one number that I don't have matching the required 7. And just like the first part of the question, the total number of outcomes is still going to be 15 choose 7. So my probability of winning matching 6 numbers out of the 7 using this probability formula is going to be equal to 7 choose 6 times 8 choose 1 divided by the total number of outcomes, 15 choose 7. And that's going to be 0.0087. What is the probability of not winning the first or second prize? So the way we calculate this is by the indirect method. And if you forget what the indirect method is, it's just simply taking all the possible outcomes and subtracting the ones that we don't want to get whatever's left over is what we do want. So it's going to be 1 minus probability of the grand prize minus the probability of the second prize. That's going to be 1 minus 0.00016 minus 0.0087, giving us a probability of 0.9914. So there is a 99% chance that we will not win the first or second prize. And that's just how usually lotteries go. All right, let's look at example 2. A group of 3 students are to be chosen from a group that consists of 7 Leafs fans and 5 Canadiens fans. If you're not familiar, these are the names of hockey teams in Canada. What is the probability that the group chosen will all be Leafs fans? So let's calculate the number of successful outcomes. So n of A is going to be 7 choose 3. Because you're choosing a group of 3 students and you have 7 possible Leafs fans to choose from. So 7 choose 3. The total number of outcomes So if I add 7 and 5, I get 12. So I have 12 total different fans. So 12 choose 3 because I'm choosing a group of 3. So the probability that you have 3 Leafs fans is equal to 7 choose 3 divided by 12 choose 3, which is 0.1591. So you have a 15 or 16% chance of having all 3 students in your chosen group to be Leafs fans. Part B, what is the probability that the group will not have only Leafs fans? So again, when you see this kind of word not, generally that indicates the use of the indirect method. So I'm going to take 100% minus the probability that I only have Leafs fans. And that will give me, okay, that will give me 1 minus 0.1591, leaving me with 0.8409. So there's an 84% chance that in my group of 3, there will not be completely Leafs fans. At least one of them will be a Canadiens fan. Okay, example number 3. So on this checkerboard, the red checker can only travel diagonally upward. It cannot pass through the square occupied by the black checker, but it can jump over the black checker. Determine the probability of the red checker ending up in each slot at the top of the board. So we kind of have to look at counting using the Pascal's triangle. How many ways are to get to each of these spots at the very top of the board? Well, the red checker can go from here to here, so that would be, so you start off the Pascal's triangle. There's one way to start off, and that's this in this square right here. There's only one way to get into this square right here, so I'll say 1. From here, I can get to this square, which is also 1, and from here, I can get to this square, which is also 1. From here, same thing on this side. I can also express these positions as 1. There's not going to be nothing going to fit in these white squares here because you cannot go backwards. You can only move upwards, diagonally. So what about this square? Well, I can go from here to here, then here, and then from here to here to here. So there are 2 paths to get to that square. I can also get that number by adding the 2 numbers below it. So 1 plus 1 make 2, just like the way the Pascal's triangle works, except this here is just going to be upside down. Same idea, I can get 3 paths here because 2 plus 1 is 3. 3 plus 1 make 4, and then 4 would continue here as well. And I can continue on this side. This would also be 3, and this would also be 4. Now, when it comes to the black square, I'm not going to be hitting the black square. I'm going to be jumping over it. So I'm going to take the 3 paths that I get to this white square. To get to this white square, I have to add the 3 paths plus the 4 paths that I have to get to this white square to make 7 paths. I can only get from this to this square by being either here or coming from over here. So if there's 4 ways to get here and there's 3 ways to get here, I can get 7 here. Similarly, I can get 7 here. And over here, I got 1 plus 4, which makes 5. And so I now have completed that row. Then if I went to the next row, 7 plus 4 is 11. 7 plus 7 is 14. 5 plus 7 is 12. And 5 continues on over here. And then A, B, C, and D would finally end up with these numbers here. So 5 plus 12 make 17. 12 plus 14 make 26. And 14 plus 11 makes 25. And then left with 11 by itself over here. So now I have the total number of ways to get to each of these 4 spots. I'm going to use those ways to calculate the probabilities to get into those 4 spots. Okay. So by the way, if you add up all these numbers, so 17 plus 26 plus 25 plus 11, you get a total number of 79. So there are 79 total paths in this checkerboard. So I need that total number of outcomes to calculate my probability. So the probability of that red checker is going to get to spot number A is going to be 17 out of 79, or 0.215. The probability that that checker is going to get to B would be 26 out of 79, or you could say 0.329. The probability that that checker is going to get to spot number C is going to be 25 ways to get there, divided by 79 total paths. which is 0.316. And the probability that the checker will get to D is equal to 11 out of 79 total paths, which is 0.139. So based on these probabilities, which one is it most likely to end up? Well, it's the one with the most paths. So therefore, I'm going to say here, therefore, the red checker is most likely to fall or to end up in slot B. Okay, let's look at example number 4. 4 people are needed to help at a party. Determine the probability that you and 2 of your 3 friends will be chosen for this job if 4 people are randomly selected from a group of 12. So let's calculate the number of ways this can happen. So counting you, you'd have 1 choose 1. You're going to have 2 of your 3 friends, so it's going to be multiplied by 3 choose 2. And then you're going to have 1 other friend. So because it's 4 people helping you. Okay, so it's you. So you plus 3 more plus 1 more. So who's left? You have a group of 12. And if you're part of that group of 12, then so you subtract 3 from your friends, you subtract yourself, so you have only 8 people left to choose from. So it's going to be 8 choose 1. So this represents you. This represents 2 of 3 friends, and this represents 1 other, and we're going to call them a non-friend. Okay, and the total number of outcomes is simply, if you have 12 to choose from, you're going to choose 4 to make that group. So my probability is going to be, just write out the formula here, 1 choose 1 times 3 choose 2 times 8 choose 1 divided by 12 choose 4. If I take a calculator and I multiply this entire top line, I would have 24. And 12 choose 4 is 495. And dividing 24 by 495 gives me 0.0485. Okay, so it gives you about a 5% chance that you would get 2 of your 3 friends chosen for the job. Now I just want to remark that 1 choose 1 is not necessary to write because it's equal to 1, but it may be helpful to have always. It's help you with your thinking as you're problem solving. Okay, let's look at example number 5. A pizza contains 3 toppings randomly selected from the following choices: pepperoni, mushrooms, green peppers, ham, bacon, and onions. Manuel enjoys all toppings except bacon and onions. What is the likelihood that a pizza will contain A, no toppings that Manuel likes? Okay, so let's look at how many toppings we have in total. Well, we have pepperoni, mushrooms, green peppers, ham, bacon, and onions. So we have 6 toppings in total. So 6 toppings total. Note, okay, so part A, there are 4 toppings that Manuel likes and 2 that he dislikes. So I'm going to write that here. So there are 4 toppings he likes and 2 toppings he dislikes. So then the number of ways you can get in the event that no toppings that he dislikes, well, is 4 choose 3. Because the pizza contains 3 toppings and there's 4 of them that he likes. Total number of possible outcomes are, well, there are 6 toppings in total and you're going to choose 3. So 6 choose 3. So the probability that there's a pizza with no toppings that he dislikes, meaning there are toppings that he likes, is 4 choose 3, and 6 divided by 6 choose 3, which is equal to 0.2, which is 20%. So 20% chance that he gets a pizza with all the toppings that he likes. Part B, what about exactly having 1 topping that Manuel dislikes? So the counting number of ways that can happen is that you can have 2 choose 1, if there's 2 that he dislikes. You're going to choose exactly one of them. And you're going to multiply that by 4 choose 2. So there's 4 toppings he does like, and we're going to have exactly 2 of them. And then n of s, total number of outcomes, is still unchanged, so 6 choose 3. So the probability is going to be 2 choose 1 times 4 choose 2 divided by 6 choose 3, which is equal to 0.60 or 60%. Part C, what about at least one topping that Manuel dislikes? At least one. So that means you could have one topping that he dislikes, or you can have 2 toppings he dislikes. Okay, so if you use the indirect method, you can solve this problem, or you can use a direct method. So let me just show you the indirect method first. So 1 minus the probability that none of the toppings that he dislikes. And that's simply 1 minus 0.20, and that's 0.8. 80% chance that he has at least one topping he doesn't like. If we did this using the direct method, we would simply calculate the probability that there be 1 that he dislikes plus the probability that there are 2 that he dislikes. And we already know from that part B that there is a 60% chance he gets 1 that he does not like. And the probability that he gets 2 he doesn't like would simply be 2 choose 2 times 4 choose 1 divided by 6 choose 3. 0.60 plus again 0.20, which is 80%. Alright, example number 6. 10 boys and 12 girls decide to rent a 16-passenger van and a 6-passenger car to drive to a concert in a nearby city. If the group is distributed randomly between vehicles, what is the probability that there are no boys in the car? And then part B, there are no girls in the car. And part C, Stephen and Susan are both in the van. And part D, and we'll take care of afterwards. Okay, so the probability that there are no boys in the car. Well, let's do a little bit of counting first. So there are 10 boys plus 12 girls for a total of 22 students. The van can hold 16, and the car can hold 6. So the probability that there are no boys in the car, meaning you only have girls. So the probability, or the number of ways you can count the successful outcomes, is simply 12 girls, and the car can only hold 6, so 12 choose 6. The total number of outcomes altogether is going to be 22 students, and you're going to choose 6 to go in that car. So the probability that you'll have only girls in the car is 12 choose 6 divided by 22 choose 6, giving us 0.0123, about a 1% chance. What about the probability that there are no girls in the car? Well, if you had 10 boys, then your number of ways you can count that would be 10 choose 6, and so the probability would become 10 choose 6 divided by 22 choose 6. Oops. That would give me a probability of 0.0028, so less than 1%. So what if Steve and Susan are both in the van? How would you count that? Well, I would need to count 1 choose 1 for Steve, and multiply that by 1 choose 1 for Susan. Okay. And so you remove those 2 people out of the count, then you have 20 left. So 20 choose. I'm going to choose 14 more people to go in the van, because the van can hold 16, and Steve and Susan are already 2 that have been chosen, so 14 more have to be chosen. And the total number of outcomes for the van is going to be 22 choose 16. So my probability is going to be 1 choose 1 times 1 choose 1. Again, you don't have to include the 1 choose 1s, but it may help you with your thinking. 20 choose 14 divided by 22 choose 16. And that's going to be 0.5195, about 52% probability. What if either Steve or Susan are in the van? Or, so it's non-mutually exclusive. Okay, so you have to look at this, where you have to count n of a, a little bit different. Okay, so what if it's Steve? 1 choose 1 for Steve times 21 choose 15. So you have to have Steve plus 15 more people. Now there's 21. So Steve plus 15 others. Okay, but you might go, well, aren't you including Susan in this count? Now you can have the possibility of both Steve and Susan. Well, I will take care of that when you do the subtraction and later on. So just bear with me for a moment. Let's add also the possibility here that we have 1 choose 1 for Susan. So Susan plus 15 others times 21 choose 15. Now I'm going to subtract the overlap. So of course, yes, you don't want to have Steve and Susan together. So the overlap is when they are together, you have 20 choose 14. So this is the overlap of Steve and Susan. Okay, and if you plug all this into a calculator and to calculate the probability, you'd find that the probability is about 0.9351, 0.51%. In part E, either Steve or Susan are in the van, but not both. So n of a equals 1 choose 1 times 20 choose 15 plus 1 choose 1 times 20 choose 15 again. So I'm adding possibility that Steve plus 15 others, not including Susan. So instead of 21 is 20. And this, I'm adding the counting of the possibility that it's Susan plus 15 others, not including Steve. Okay, and that probability is going to be 2 times 1 choose 1 times 20 choose 15 divided by 22 choose 16. 41.56%. Okay, and that ends this section.